Hi everybody, my name is Danielle Weigel, and today we are going to be working through a homework problem for Transport 2 relating mass diffusive flux to molar diffusive flux. Let's go ahead and look at the situation at hand. We have a closed system of a capillary tube, and that capillary tube is split in half, and we have ideal gas A on one side and ideal gas B on the other. When we remove this division right here, the two gases are going to start diffusing together. We know that pressure and temperature remain constant and uniform throughout this diffusion process until they reach equilibrium. Or we know that these two components are going to be reaching equilibrium and the pressure and temperature will remain constant and uniform. The point of this whole situation is that we want to derive an expression relating the mass diffusive flux to the molar diffusive flux of component A. And we want to use the mass fraction of A and the molecular weights of A and B. So that's what we want to get to. So let's start out by just looking at what we know about flux in this situation. Fluxing is an amount of material moving across a certain distance per time. So when we're looking at, let's say, just the total molar flux of this system, we know that because this is a closed system, nothing's escaping, the amount of material passing through a certain point per time has to be 0, because we have all these molecules of A over here and all these molecules of B over here, and they're going to start moving across this boundary, if the boundary that we removed. So let's just say this point in time right here. If you have a bunch of moles moving, if you have more moles moving to the left here than you do to the right, then you're going to get a buildup of moles on the left, and that's not uniform equilibrium. So by that logic, we know that the molar flux has to be 0, the total molar flux. And we're going to go ahead and relate this molar flux to the molar diffusive flux. We know that the mole flux of component A is equal to the mole fraction of A times the total molar flux plus the molar diffusive flux of A. That's our relationship. And we know that because this is a closed system, the total molar flux is equal to 0. That means that this bulk contribution is equal to 0, and that just means that the molar flux of this component is equal to the molar diffusive flux of this component. And we want to relate this molar diffusive flux to the mass diffusive flux. If we just go ahead and look at the mass flux versus the molar flux, it's a really easy relationship, just an amount of material moving across a distance per time. It's just the weights of the materials that's different. So that relationship is really easy. It's just the mass flux is equal to the mass fraction of, or not mass fraction, molecular weight of A times the molar flux of A. That's a really easy relationship. But we can't say the same for the molar diffusive flux and the mass diffusive flux. And as we work through these equations, you're going to see why. Let's go ahead and define the mass diffusive flux and the molar diffusive flux. When we look at we'll start with the molar diffusive flux of A. We know that that is equal to the mole concentration of A times the velocity of A minus the molar average velocity of the system. And we know that the mass diffusive flux is much the same. It's just in terms of mass. mass diffusive flux of A, component A, is going to be equal to the mass concentration of A times the velocity of A minus the mass average velocity of the system. So let's go ahead and look at this molar diffusive flux definition. Since we know that the total molar flux is 0, like we said right here, we know that the average velocity, molar velocity of the system is also going to have to be 0, and that is because of this relationship right here, that the mass flux is just going to be equal to the concentration times the velocity. And that's just because it's the amount of moles moving across a distance. You got distance per time, and you got your amount, your moles right here. And that's what this is, moles crossing a distance per time. That's their relationship. So you know that this is equal to 0, which is really handy dandy because then you can simplify this expression right here. For the molar diffusive flux is equal to the molar concentration of A times the velocity of A. And then we can just go ahead and rearrange that so that the velocity of A is equal to the molar diffusive flux of A divided by the molar concentration of A. And then we can plug that into this equation right here of the definition of the mass diffusive flux. And already, right off the bat, we've already got an equation relating mass diffusive flux to molar diffusive flux. And now we just want to simplify it so that we've got our other equation or other variables to be the mass fraction and the molecular weights of both components. So let's go ahead and write out that equation. The mass diffusive flux is equal to the mass concentration of A times the molar diffusive flux of A divided by the molar concentration of A minus the mass average velocity of the system. So let's go ahead and distribute in this mass concentration of A, and that will give us this equation right here, where we have mass diffusive flux is equal to the mass concentration of A divided by the molar concentration of A times the molar diffusive flux of A minus the mass concentration of A times the mass average velocity of the system. We don't need that there anymore. Let's go ahead and look at this relationship right here. We know that a mass concentration of A, or just a mass concentration in general, divided by the molar concentration is going to be equal to the molecular weight of that component. So we can go ahead and simplify that right here. The mass diffusive flux of A is equal to the molecular weight of A times the molar diffusive flux of A minus the mass concentration of A times the mass average velocity of the system. Let's go ahead and we have these in the terms that we want finally, but this one is not. So we're going to look at this section of the equation right here. Specifically, let's start with the mass average velocity. The mass average velocity is defined as the summation of the velocity of the components times their mass concentrations, all divided by the summation of the mass concentration. That is just the definition of that mass average velocity. So for us, that's going to look like this. The velocity of A times the mass concentration of A plus the mass concentration, the velocity of B times the mass concentration of B, all divided by the total mass concentration. So let's go ahead and stick that into our equation. The mass diffusive flux of A is equal to, the molecular weight of A times the molar diffusive flux of A minus the mass concentration of A divided by the total mass concentration times the velocity of A times the mass concentration of A plus the velocity of B times the mass concentration of B. So let's go ahead and look at these velocity definitions right here. We've already looked at what these substitutions for these velocities up here in this equation right here. So and that's great because that puts it in terms of molar diffusive flux and molar concentration. So let's go ahead and swap those out. And that's just going to give us molar diffusive flux over molar concentration of A and molar diffusive flux of B over concentration of B. We will write that out really quick. Let's look at, before we do that, we'll look at this relationship right here. The mass concentration of A over the total concentration. We know that the mass concentration of a component or the total mass concentration is going to give us a mass fraction, which is one of those variables that we want in the end. So that's great. Let's put that into our equation as well. Mass concentration of A times the mass concentration of A over the molar concentration of A times the molar diffusive flux of A plus the mass concentration of B over the molar concentration of B times the molar diffusive flux of B. So we're going to look at two substitutions right here. We've already done this substitution before, this mass concentration over molar concentration, and we know that that gives us molecular weight. So we're going to swap those out. Molecular weight of A, molecular weight of B. And then we also know that, just like before, the summation of the molar diffusive flux components is going to be equal to 0 because they have to even out. So that just means that the molar diffusive flux of A has to be equal to the opposite of molar diffusive flux of B and vice versa. And we're going to go ahead and plug that in right there. Here we go. Mass diffusive flux of A is equal to the molecular weight of A times the molar diffusive flux of A minus the mass fraction of A times the molecular weight of A times the molar diffusive flux of A minus the mass molecular weight of B times the molar diffusive flux of A. Then we can go ahead and pull out these molar diffusive fluxes to just simplify it down. And we will get the mass diffusive flux of A is equal to the molecular weight of, we'll put this right here, molar diffusive flux of A times the molecular weight of A minus the mass fraction of A times the molecular weight of A minus the molecular weight of B. And so that is our final relation equation. When you go ahead and look back to what we were talking about at the beginning, just comparing it to mass and molar fluxes, you can see, here I'll write it out really quick, the mass flux of component A is just equal to the molecular weight of A times the molar flux of A. You can see here that if the two molecular weights of components A and components B are the same, then this equation right here, you can see right here, that it would be what you would expect. But if they're not, then that's not the case. So that gives us our final relationship equation right here. I hope this helps everybody. If there are any questions or comments, go ahead and leave them in the comments down below. Have a great night, everybody.